Okay, let's go back to the Flatlands and try to explain the notion of geodesics. So first of all, geodesics are parts of great circles on the sphere. So that sort of means that we have to explain what great circles are. The first thing to notice is we computed the distance between this point and that point, the spherical distance, using that formula, and it came out to be pi-fourths. And you might ask whether, if you travel from this point to that point, whether you should go along this. And by now you already know that you shouldn't, right? Because that here, so I'm just write pi-fourths beneath, that piece here is not part of a great circle on the sphere. In fact, on the sphere, it's one of the latitudes. That blue bit here is part of that latitude over here, where the angle here is pi-6. Okay, and this is not a great circle. Where is a great circle? So it turns out that, you remember, if you go a little bit higher, then the distances become a little shorter, even though they look longer here. So probably geodesic between these 2 points is something like this. And of course, you know, that's just part of a great circle. So you might ask yourself, well, how do then great circles look like on this, if you were to explain geodesics? So let's just draw a few of them. So first of all, this is a great circle. The equator is one of the great circles. And suppose I start off from here, and I'm trying to now fly along a different geodesic. So if I stray a little bit away from the equator, this would correspond to a great circle in the sphere that is slightly tilted with respect to this plane. Yeah, if you go a little further up, so you start here and you try flying a little bit further north, then you get another one like this. These are not sine curves. They are different types of curves. And in fact, as you get closer and closer, if you try to fly further and further north, they become almost rectangular shaped. So these are the great circles. In other words, they are examples of geodesics on the sphere. So this is how we could explain to these mathematicians in the Flatland what the geodesics on the sphere look like. No contradiction in this. You've developed now a theory of a sphere without ever actually drawing or having to imagine a sphere. It is helpful to have to imagine the sphere. This first mathematician, we said, had a three-dimensional imagination, so he was able to dream of a sphere and then sort of come up with all these formulas. But to be honest, if you just wanted to, you could have never been able to imagine the sphere and just work off this rectangle and say, okay, a sphere is that rectangle. You just connect these two, you just identify these two. These two are points, and then this is the length of a curve. In fact, what this would recreate is it would recreate exactly the distances on the sphere. Okay, so two reactions to this. If you are a beginning mathematics student in the Flatland, you would say, well, duh, but this is useless. We all know that the world is flat. Somebody created this geometry they call spherical geometry. Spheres do not exist. They're quite useless. And you could have imagined this could have been a reaction of a beginning mathematics students on Earth as well, because all the geometry we're used to, the geometry we're most used to, is the planar geometry. However, you can't claim this is useless in our world. Just ask any pilot of a plane. If you go on any flight, or even look online for a flight map, you would see that you have these two cities the Earth looks like this on that map, and then you have these two cities, New York, London, and the geodesic between them, looking like this. Right? The pilots never fly in straight lines because straight lines on this flat representation of a sphere are not geodesics on the sphere. They are not straight lines on the sphere. This is just not the greatest representation. It's a model of a sphere. It's a two-dimensional flat model of a sphere. There is another remark I wanted to make here, is that right after that, we're going to be studying another type of geometry, namely hyperbolic geometry. And in that case, it will be us who will be like these people in Flatland, not being able to imagine a hyperbolic plane. Instead, we're going to use a model for a hyperbolic plane that will be really quite similar to this. We're going to take a plane and we're going to distort distances on that plane. And we're going to say, well, that is a hyperbolic space, a hyperbolic plane that I cannot really imagine, but I can describe it mathematically. And that's one of the powers of mathematics. We want to be able to imagine spheres that are not only two-dimensional, but three-dimensional, five-dimensional, and dimensional. We want to be able to imagine other geometries, like the hyperbolic geometry, that we cannot just take, like we have this nice two-dimensional model of a sphere embedded in the three-dimensional space, and sort of look up everything there. We actually have to work from models like this, from these imperfect models that will just sort of make a picture on the plane, and we say we'll distort distances in a different way from this. Right? If I distort distances in this way, I just get the geometry of a sphere. But there's a way to distort distances in a different way to get to some new geometry, which is called the hyperbolic geometry.